Okay, welcome back. This is the sixth video in the playlist that deals with calculations involving chemical equilibrium, and it's part of the general playlist that deals with chemical equilibrium in general. Now, in the last video, what I did was I introduced the concept of Q. And Q is a concept that we use when we're provided with a chemical equation in which all of the components are combined in a reaction vessel at the same time. And the challenge for finding the equilibrium concentrations of a species in that case is that we first have to determine which way the reaction is going to shift to reach equilibrium. So just to reiterate what we did then, the Q is a value that's calculated identical to K. The difference is that we're plugging in the initial concentrations, non-equilibrium concentrations of the material, and we're literally taking the ratio of products divided by the reactants based on the law of mass action. So the Q literally is calculated exactly the way K is, but the difference is that in the case of the reaction quotient, and I should probably write that down here, in the case of the reaction quotient, the concentrations that we use to generate this ratio are non-equilibrium, and usually they're initial concentrations found or provided in the problem. So in this problem, you see that we've been given 1 molar Br2, 1 molar Cl2, and 1 molar BrCl, all of these in the reaction flask at the same time at some fixed temperature. And what we learned when we calculated the Q was that Q is equal to 1 in this case. Q is greater than Kc, and because Q is greater than Kc, the reaction has to shift towards the left or towards the production of reactants. So we know that the reaction needs to shift to the left. The reason that it does is because the proportion of products divided by reactants is much higher under the circumstances in which this reaction has been set up than the equilibrium expression that you find at equilibrium. So in other words, the amount of products at the beginning of this problem, before equilibrium, so this is non-equilibrium, is much greater than the concentration of products that are found at equilibrium. So reaction shifts left. Okay, now we know which way the reaction is going to go. So now what we need to do is set up our ICE table, or in my class I call it the box. So this is the situation we have before any reaction. Now, at equilibrium, and I usually show that this way by just writing the word after, since we know the reaction is shifting to the left, then what's going to happen with the BrCl is that we're going to have 1 molar, and it's got to decrease by, all right, notice the coefficient is 2 here, so it's going to decrease by 2x. Each of the reactants, though, are going to increase by a factor that is dependent on their coefficients, and their coefficients are 1. So it's going to be, for the Br2, it's going to be 1 molar plus x, and for the Cl2, it's going to be 1 molar plus x. Okay, so now we have a situation which allows us to solve for the equilibrium concentrations. And so let's go ahead and set up our expression. So Kc equals 1.11 times 10 to the minus fourth, and the numerator is going to be 1 molar minus 2x, and that quantity is squared. And then in the denominator, just shorten this up a little bit. All right, in the denominator, we're going to have 1 molar plus x, and that quantity is squared. Now, you look at this, and at first glance, it's like, oh my God, we have a quadratic equation again. which is really a pain in the neck to solve for. However, recognize that in essence though, like a previous example that we did, this is a perfect square. So we can take the square root of both sides of this, and that will eliminate the fact that will eliminate the possibility that we have to actually use a quadratic formula. Okay, so I'm going to go ahead and just jump right to what the square root of 1.11 times 10 to the minus fourth is. So this is going to be 0. It's going to be 0.0105 3565. Okay, and that is equal now to 1 molar minus 2x divided by 1 molar plus x. So at this point we've got a problem that's a lot less complicated than it was a minute ago. All right, and now it's just for the algebra. Okay, so I'll go ahead and multiply both sides by 1 molar plus x. So this is going to be 0.01053565, and that's going to be times quantity 1 molar plus x. And that whole thing is now equal to 1 molar minus 2x. Okay, now I'm going to go ahead and rearrange this. So I'm going to have 2x on this side, and it's going to be plus 0.01053565x, and then that whole thing is going to be equal to 1 minus 0.01053565. Okay, now on this side we're going to end up with 2.01053565x. A lot of numbers here. And then 1 minus, all right, so we're going to end up on this side with 0.98946436. Basically all I'm doing is I'm holding all the numbers on my calculator screen so that we don't have to worry about significant figures. And then finally my x value is going to be 0.492139.6. This should be the x value. Alright, now let's go ahead and calculate our equilibrium concentrations. So the Br2 and the Cl2, which are equal, are going to equal 1 plus 0.492139.6, and so these guys both equal 1.49 and change. That's the molarity of these. And the concentration of the BrCl, okay, is going to be equal to 1 minus, 2 times the x value, which is 0.492139.6. Okay, so the BrCl is going to equal 0.0157206 molar. Now, notice that that particular value is a lot smaller than the values for the Br2 and the Cl2. But going back to the top of my screen here, remember that your Kc value is 1.11 times 10 to the minus fourth. And in the previous video, I pointed out that at equilibrium, therefore, the ratio of products to the reactants is 1 to 9,009. So there should be a very small amount of BrCl in this reaction mixture when we're done, by comparison to the Br2 and the Cl2. Now, as a last thing, what we're going to do is make sure that we did not make any mistakes here. And to do that, I'm going to recalculate the Kc value using the numbers that we actually established. So in the top here, it's going to be 0.015726. That quantity is squared, and it'll be divided by 1.492136, and that quantity is squared because we've got two of the values, Br2 and Cl2, and the grand total is 1.109 times 10 to the minus fourth, and you see that there's a beautiful correlation between that and the original the actual equilibrium constant that we were given at the beginning of the problem. Okay, so to finish, the crucial thing in solving a problem like this, a problem where you're given concentrations, initial concentrations of all the components in the chemical reaction, the first thing you need to do is calculate Q and figure out which way the reaction is going to shift. Once you know which way the reaction is going to shift, you've got to build your ICE table, or I call it the box. All right, and build your equation, and then you set up your Kc like you have for all of the other problems that we've worked, and then hopefully you'll have some kind of trick that will allow you to reduce this to something manageable. If not, your only option is going to be to utilize the quadratic equation. Find the equilibrium concentrations, and then as a test, plug in those values back into the equilibrium expression and make sure that you get a number which is very close to the actual equilibrium constant that was given in the problem. All right, and with that, I'm going to go ahead and close this video.